Look closely at a slab of concrete. At a microscopic level, its atomic lattice is vibrating violently. The rigid infrastructure is in constant, invisible motion. This motion is driven by thermal expansion. As materials absorb heat, their kinetic energy increases, and atoms push further apart. When they cool, they contract. On a macro scale, the results are destructive. If a long concrete slab has no room to grow, that internal energy has nowhere to dissipate. The resulting stress causes the material to buckle and crack. The expansion joint acts as a structural safety valve. By leaving an intentional gap and filling it with a compressible elastomeric seal, engineers allow the concrete to expand safely without colliding. This provides the same flexibility found in a pair of stretchy jeans. While rigid denim restricts your movement the moment you bend, stretchy fabric incorporates flexible threads that move with the body. Without these deliberate gaps, the natural thermal cycles of the planet would tear our modern world apart from the inside out. This physical reality is most volatile in high-pressure industrial environments. Inside a steam pipe, temperatures can surge to 1,000 degrees Celsius. A 50-meter run of steel pipe will grow 60 millimeters as it reaches operating temperature. If that growth is restrained, the resulting pressure will destroy connected turbines and fittings. This chart models allowable building lengths relative to design temperature changes. As the temperature change increases, the safe length of a rigid structure decreases significantly. In these extreme environments, engineers utilize metal bellows to manage the growth. These joints are made of thin corrugated stainless steel. The convolutions compress like an accordion to absorb thermal expansion while maintaining a seal against lethal internal pressure. The bellows serve as the primary defense, protecting high-temperature systems from their own self-generated destruction. Further down the line, thermal growth is replaced by mechanical vibration. Near massive industrial pumps, the entire system is in a state of high-frequency agitation. In these zones, metal joints are prone to fatigue. Constant lateral vibration causes the thin steel to work harden and eventually snap. Here, the rubber expansion joint is the superior solution. These joints use resilient elastomers reinforced with fabric plies and steel rings. This composite structure provides flexible, multi-directional shock absorption that metal cannot match. This material provides acoustical impedance, dampening mechanical vibration by up to 90%. This significantly reduces the transmission of noise through the connected piping. While metal contains the heat, rubber joints are the shock absorbers that prevent the system from shaking itself to pieces. On a macroscopic scale, environmental forces become even more complex. A bridge deck must survive extreme temperature swings while handling dynamic traffic impacts. When movements exceed several hundred millimeters, engineers deploy modular expansion joints. These systems can handle displacements exceeding 1 full meter. The assembly includes aluminum plates and stainless steel centering bars. These bridge the gap to provide a continuous, safe surface for vehicles. Beneath this primary structure sits a secondary water barrier. This keeps corrosive de-icing chemicals and water away from the bridge's internal supports. By distributing movement across multiple sealed gaps and support bars, the modular system ensures no single opening becomes a hazard to traffic. These act as engineered buffers, decoupling massive structural elements to prevent compounding forces from triggering a total collapse. Across a sprawling metropolis, billions of tons of infrastructure are expanding and contracting simultaneously. Large-scale buildings utilize separation joints to divide the structure, ensuring that different sections can settle and shift without stressing the neighbors. These joints slice through the entire frame. This separation continues through to independent foundation blocks, preventing cracks caused by differential settling. This principle is repeated across the entire city, from skyscraper facades swaying in the wind and even to airport runways resisting surface deformation. Over a 24-hour cycle, the city swells and shrinks. Every bridge, pipe, and building is breathing in sync with the rising and falling temperature. Without these hidden flexible zones, the modern world would buckle and snap under the pressure of its own weight and the elements. Modern infrastructure is a dynamic, moving machine.
surviving only because of the engineered spaces left between.